students cannot join the class, we can get a recording. All right, let me bring up the logical efforts here. Um, Actually, the other one, right? This guy. Okay. All right. I think the time is up. Let's go ahead and get started. All right. So last class, um, remember we go through this very important equation, right? So in order to calculate the delay, right? So the best delay, right? So I mean, if you try to design the faster circuit, right? So with the least amount of delay time, this is the conclusion, right? This is the most important message that we want to deliver in the last class, right? So if you have a multi-stage design, make sure each of the stage bear the same amount of the effort delay, right? So which means you have a small f, right? So um, is which is the effort delay for each of the stage, right? Each of the you can see a stage delay as well, right? But each of the stage they will bear some amount of the effort, right? So then if you can do that, right, the total the multi-stage circuit will have the minimum delay time, right? So each of the stage delay will be the f to the power of 1 over n, right? So remember we discussed that last time, right? F is the capital F is the total past effort, right? So F is equal to GBH, right? Remember we discussed that as well, right? So instead of a G and H, right? Small g and small h for single stage. For multi-stage, right? The capital F is equal to a capital G times capital B times capital H, right? So if you calculate the total F, and then you use the one to the you to the power of 1 over n, right? So then you should be able to divide them, yeah, equally into a n, yeah, n part, right? So number of n parts. So and if you multiply by n, right, because that will be the total the past effort, right, in that stage, right, plus the total p, right? So the parasitic delay, right? So you will get the delay time. This equation will give you the minimum amount of the delay time that you can achieve for a specific multi-stage circuit, right? So this, yeah, again, right? So this equation give you the minimum delay time that you can achieve for certain circuits when with multi-stage. All right. Okay. And the each of the stage effort will be like F equal to capital F to the power of 1 over n, right? So, and we discussed one example here, right? Remember, this is one of the example we show in the last class, which have a three stage, right? So remember the why there's a three stage, right? So this is a NAND gate drive, a three NAND gate in parallel. This is the first stage, and another NAND gate, three input NAND gate drive a NOR gate, second stage, and NOR gate drive a output capacitor, right? So that is the loading, right? That is the last stage, right? So you have a three-stage design here, right? And the design has been given the input capacitance value, which is the 8, right? So if you consider this a blue path, right? The blue path is what we try to optimize, right? We try to achieve the minimum amount of delay time, right? So we have input capacitance 8, we have output capacitance 45, right? And we know the topology, right? We know the what kind of the gate that we can use here. We know how many number of stage, right? What we don't know is the size of the second stage, sorry, the first stage loading and the second stage loading, right? So if we don't know the size, and in order to achieve the best delay time, right, how can we determine the size of the X and the Y, right, which is the input capacitance? And we from the X and Y, we can calculate the transistor size, right, for PMOS and NMOS, right? So that is the example, right? Very good examples. We discussed that, right? So on a higher level, you can consider, right? This is the path that we need to consider, right? So the delay time D, right? So let me go back to the equation here. Right, here's the important equation here. Um, because we know the topology and we know what kind of a gate it is, right? So that we are able to we are able to calculate the capital G, right? Remember, in order to calculate the least amount of the delay time, to get the minimum delay time, we need to calculate this small f, right? Remember, yeah. If I go back to the equation here, we need to calculate the small f, right? So small f is coming from the capital F, and you get a number of stage, right? Here we identify the number of stage is equal to 3, right? So whenever we got f, capital F here, we just use the capital F to the power of 1/3, and we should be able to get the each stage delay, right? So okay, so how can I get a capital F? Capital F is capital G times B and H, right? So if you go back to the example here, capital G is each of the input stage, that the logical effort, right? So you have the capital G here, and you have it is equal to G1 times G2 times G3, right? G1, G2, G3. We go through that, right? How to calculate that. Yeah, even though you don't have the table, right, you should be able to calculate the G1, G2, G3 by yourself, right? Because you need to identify what is the transistor level schematic for that particular gate, right? And identify and then identify the PMOS and NMOS size, right? So that the P network and N network, the effective resistance is equal to R, right? And then you get the total input gate capacitance divided by the unit inverter, right, input capacitance, well, which is equal to 3, right? So then you were able to get the G1, right? Then G2 and G3, right? You get a capital G, and then GBH, right? B will be the branching effort, right? From this one, this is a 3 branch here, 2 branch here, and each of the branch, they have the same capacitance, right? So the B1 is equal to 3, B2 is equal to 2, right? So you have the branching effort here. Okay, and then you have the pass effort, right? Which is you can calculate the GBH. H is the electrical effort. That is the simplest one. You don't have to worry about intermediate stage, right? You just need to calculate the output capacitance divided by the input capacitance, right? Which is 45 divided by 8. Now you have the GBH value. You were able to calculate the F, right? Once you have the F value, capital F value, and you can get the best stage effort, which is the capital F to the power of 1/3, right? 1/n, right? So that is, in this case, number of stages equal to 3, right? So you use F to the power of 1/3. So that is 5, right? Okay. So you have the small f values, right? You should be able to, and we calculate the parasitic delay, right? So for each of the stage, similarly as we did for the logical effort, right? Once you have the schematic, transistor level schematic, and the size and transistor size, you should be able to calculate the parasitic delay, right? For each of the input stage, right? So you add them together, right? So difference is total parasitic delay is the sigma, right? So you add them together. Yeah, capital G is the multiplier, right? This is the difference, right? So parasitic delay, you add them together, right? Do not multiply the parasitic delay, right? Just add them, and you get the total 7 right here. And then the minimum delay time is using that equation, that very important equation, right? N times to the F to the power of 1/n, and then plus P, right? So that is the and number of stages 3, right? Best stage effort, we can calculate it from here. Small f, right, which is 5, and then you get the 22, right? And compared to the fan out of the 4, like an inverter, this FO4 means if you use one inverter to drive a 4 inverter, right? Which we discussed in the last class as well, right? One of the is kind of the standard block as well, right? So fan out of the 4 inverter. You can calculate the stage delay as well, right? So, okay. So with this method, right, you should be able to calculate the minimum delay time, right? So, okay. In addition to that, we also discussed there. Okay, if I know what is the minimum delay time is right from this schematic, right? But we can how can we determine the size of the x and y to achieve this delay, right? So that is another questions, right? How can we calculate that, right? So if we can back calculate the size, right? For example, we can start to calculate on the third stage, right? Last stage, right? Why we want to do that? Right? Because the last stage, we know uh, the output capacitance value, right? So what we don't know is the input capacitance value, right? So, okay, you may wondering, okay, I can calculate electrical efforts, right? But that is not what we want, right? So what we can calculate is the stage effort, right? Small f, right? Remember, we get a small f from this equation, right? We get a small f from this equation, from the total passed, right? And yeah, to the power of 1 over n, right? We get a, if that's the stage effort, right? So that means when you're using this first stage, second stage, the third stage, all three stage have the same stage effort, right? So that means first stage F1 is equal to F2 is equal to F3. All of the three stage effort is equal to 5, right? For this case. Okay, so now let's back calculate that, right? For the last stage, F3 is equal to 5. So F is not only equal to this guy, right? This is what we derive the best stage effort, right? But the definition of the stage effort, small f, is equal to G3 times H3, right? So that is what we use to calculate the size here, right? Just a small f. Okay, so if you go back to here, right, you will find out, okay, you have the G here, right, and the Y is, it didn't show the equation here, right, but the F is F3 is equal to G3 times H3 is equal to 5, right? So we have a 5 here. So you know the F value, right? So the G3 times H3 will be equal to 5, right? G3, we know that, and H3 is what we need to calculate the size, right? Which is Y. Okay, so that we know the output is 45, right? So the H3 will be equal to 45 divided by Y, right? So 45 divided by Y will be equal to G3 divided by the F3, right? So you use that equation to back calculate the size of Y, right? The size Y is equal to 15, right? Once you get a 15, and that means the input capacitance connected on this node, right? If you can see my mouse here, right? Input capacitance connected on this node will be a 15, right? So now the next question is, that 15 is the total input capacitance, does not represent the size of the PMOS and NMOS, right? So then we need to determine the size of the PMOS and NMOS by understanding the P and N ratio, right? For the NOR2 gate, right? So I remember the NOR2 gate is PMOS. You have a two PMOS, you have a two NMOS, because this is two inputs, right? So two PMOS should be in series connections, right? For the NOR gate, right? So NAND gate is PMOS is in parallel, right? But NOR gate, PMOS in the series connection, NMOS in parallel, right? So in your mind, right, you should be able to draw a schematic, right? Two PMOS in series, two PMOS, two NMOS in parallel, and the size will be 4411, right? So that the P network effective resistance equal to R N network, right? No matter which NMOS turn on, the effective resistance equal to R as well. All right, so that is you get a 4411. So that PMOS and NMOS ratio is 4:1, right? So if you have a PMOS NMOS ratio for this particular gates, and you know the one input's total capacitance, which is the PMOS capacitance plus NMOS capacitance, right? Which is equal to 15. Then you should be able to determine the P and N ratio, right? And the P size and N size, which is 12 and 3. Okay, so then you have this, you calculate the last stage, and you can do a one more stage, right? To the second stage, you should be able to, you use this output capacitance value as a 15, right? And then you back calculate the H2 here, right? H2 here for this stage. So H2 is using the output capacitance divided by the input capacitance. I know the output is 15 calculated from here, right? X is my input, right? So the 15 divided by the input is my H3, right? And the H2, right? H2 times the G2, right? I know the G2 value, right, is equal to F, small f, which is equal to 5, right? So now I can back calculate X as well, right? So once I have the X value, and I do the similar analysis to figure out the P and N ratio, right? So and for this 3 input NAND gate, right, there will be a 3 PMOS in parallel, right? So all of the PMOS should be equal to 2, right? So that the P network, the resistance, right, effective resistance for the P network will be equal to R. And you have a 3 NMOS in series, right, from the output to the ground, right? That NMOS size has to be equal to a 3, right? So that the total effective resistance is equal to R, right? Okay, so I posted a homework online. I hope you guys can do some practice there, right? So for all this the calculation, right? Not only just try to calculate the the minimum delay time, right? But also okay, how can I calculate the G, right, value and the P value here, right? So in order to calculate the G, how can I determine the size of the PMOS and NMOS, right? So that is all being need to be practiced, right, in the homework 3. All right. Okay, so that is example we have discussed in the last time, right? So very important examples, right? Practice that. You can start to practice in the for this this lecture notes. We have these examples. Yeah, you can start it from here, right? Let's see how can I calculate that, right? So then you can do the homework as well, right? So that's my recommendation. All right. Any questions so far, right? Before I move to the next topic, right? Which is the best number of stage, right? So this example is give you the number of stage, give you the topology, right? And try to figure out the size of the PMOS and the MOS so that you can achieve the best delay time, all right? So any questions so far? And let me go back to the chat message, right? Okay, if you have any question, you can type in there. Yeah, I'm not sure if this give me some sound alert or not, right? But I will periodically check back, right, to this section, and we'll discuss. Okay, let's come back to the lecture notes. All right, the next topic is the best number of stage. All right, remember the question I raised at the beginning, right, before we start to talk about the logical effort, right? So remember the question I raised at the beginning is always the one number of stage, right? Is the single stage always better than the multi-stage, right? So yeah, you might want to wondering, right? Because for this case, for example, right on the right hand side, you have a driver, right? Single stage on the left hand side, right? This is a single stage. You have initial driver, you have a path, you have a loading, right? Which is a 64. Driver size is 1, right? And this is the second stage, the 2 stage, 3 stage, and 4 stage, right? So before you learn the optimized anything, right? So optimize this number of stage, right? So intuitively, you might think about, all right, this is a single stage, right? Use less number of transistor and pretty straightforward. You don't have anything in the middles, right? That means you don't have any additional like input capacitance and parasitic capacitance there, right? It looks like this one maybe give us the best delay time, right? Because this number of transistor definitely is smaller, right? So yeah, before we learn this class, right? So if we are staying in the software level, right, class, we always discuss the best number of the best design is the less number of transistor, right? So yeah, we always think about less number of transistor may give you a best delay time, right? So yeah, let's take a look at for these examples, right? And we can calculate this 4 case, right? We can calculate this 4 case, the delay for this 4 case, and then we can compare between them and see is the single stage always the best, right, or not, right? So let's prove it. All right. So why we are able to calculate the case right now, right? See, yeah. For single stage, no problem, right? For single stage, we use the equation is the d small d is equal to f plus p, right? F equal to a g, small g and h, right? And plus p, right? That is the single stage delay calculation, right? For multi-stage, for multiple stage, right? We know this is 2-stage, this is a 3-stage, this is the 4-stage, right? So for each of the case, we should be able to calculate the best delay time um, uh, with this particular design, right? Why we are able to do that? Because we learned this equation, right? So let me go back to that equation that we have, that very important equation here, right? So this is the minimum number of stage delay, right? So with the equation, right? As long as you make the every stage, the effort, right? Stage effort is equal to each other. And then this is the best delay time you can achieve for that particular circuit, right? For example, for the case we just discussed, right? We have a 2-stage, we have a 3-stage, right? We just need to make sure, right? So we make each of the stage effort equal to each other, and then you just use this equation to calculate the total number of stage delay, right? So we can repeat that for the 2-stage, 3-stage, and the 4-stage, right? In this case, we know the input size, we know the output capacitance, we know the topology, right? There's no branching effort, right? This is all inverter, right? So we don't have to calculate the G as well, right? The G and P all equal to 1, right? No matter what size it is, right? So let's do a calculation to estimate the delay time, all right? Okay, let me switch to um, the whiteboard, right? So you're able to see my screen, right? So yeah, 64 as the size is 1, and the case is something like this. You have the driver here. Sorry, let me double check, right? I shouldn't use a diode. I draw the wrong one. And this is the diode symbol, which is not the inverter symbol. Oh, I try to do some so I can do this. Okay. Okay. Anyway, yeah. So the eraser is not working. Right? I cannot erase it. Okay. Anyway, all right. So let's just keep doing that. I try to not to make any mistake, right? For the single stage, right? So remember the D is equal to F plus P, right? So that's the equation F equal to GH, right? Plus the P. Single stage, we should be able to calculate the delay time, right? The G is equal to for the inverter, right? G is equal to 1, right? And H, what is the H value? H is going to be the output capacitance, right? Divided by the input capacitance, right? And divide by and adding the parasitic delay, which is the 1 as well, right? For the inverter. Okay, so I think I can do this. Okay, yeah, I think it's better. As I redraw that a little bit. Anyway, yeah. Okay, so this one, the total delay time is the 64, right? So that is a pretty straightforward for the single stage. For the second stage, a 2-stage design, right? If the size is 1, and I don't know this second stage, the topology, sorry, the size of the second stage, the second inverter, right? But we know the loading, right? Remember the equation is D equal to N times the F to the power of 1 over N plus P, right? So in this case, N is equal to 2, right? So D should be equal to 2 times the F to the power of 1 over 2 and plus P, right? So this is, let's calculate the capital F, right? First, capital F for this case is the GBH, right? So that equation will not be changed for no matter what kind of circuit you're going to use, right? So capital G is equal to what, right? So let's use G is equal to G1 times G2, right? And G1 times G2 is equal to 1 times 1 equal to 1, right? Because both of them are inverter, right? So you don't worry about that. Yeah, what is the logical effort, right? So yeah, for the logical effort for the inverter is always 1, right? And B, what is the B value here? There's no branch here, right? The B value is going to be 1 as well, right? And the capital H will be the output capacitance divided by the input capacitance, right? Is equal to 64. All right. So the capital F will be the GBH together will be the 64, right? So the D value will be the 2 times the 64 square root, right? And plus P. P will be the P1 plus P2, right? P1 plus P2 is what? Is 1 plus 1, right? Okay. So the value is what? 2 times 8, right? So what? Plus 2. Right. So what is the delay time? Best delay time I can achieve for this guy is 18. Right. So if you compare this guy and this guy, you should be able to tell, right? So two stage, right? In order to to compare the two stage with a single stage for this particular case, right? For this particular case, single stage, the delay time is 64, right? For two stage, the best delay time I can achieve is 18, right? So it's already better than a single stage, all right? Okay, so and you may wondering, okay, how can I pick the size of the this second inverter, right, to achieve this best delay time? I remember the example we just went through, right? So we know the stage, the best stage effort, right, which is the small f, right? In this case, small f is equal to capital F to the power of n, right, which is 8, right, which is equal to 8. So the for the second stage, right, F2, right, is equal to G2 times H2, right, which is equal to 8, right? So G2 we know that is 1, right? H2 is 64. If I assuming this is X value, right? 64 divided by X is equal to 8, right? So the X should be equal to 8 here. Right, so the total capacitance for the inverter, right? I should put 8. So the PMOS and NMOS size will be what? Is PMOS and NMOS ratio for the inverter is 2 to 1, right? It's 2 to 1. What is this? Okay, sorry. Okay, yeah. So we have 8 is the input capacitance, right? So the P is N, right? P is equal to 8 times the let me just put it here. All right. P is equal to 8 times the 3 over 2, right? And N is equal to 8 times the 3 over 1, right? So that is the P and N size for the inverter. Okay, right? So we can calculate the two stage, which is actually much better, right, than the single stage. All right. And you may be wondering, what about the 3 stage, right? Can we keep improving the delay time, right, by adding one more stage? All right, let's do the calculation again. All right. The equation will be the same thing, right? D is equal to N times the a capital F to the power of 1 over n, right, and plus the capital P, right? So in this case, n is equal to 3, right? We have a 3-stage here, right? So in order to calculate the D, we need to calculate the capital F, right? Capital F is the GBH, right? In this case, G is still equal to G1, G2, G3, right? G times multiply them together, right? G1, G2, G3. Total the logical effort will be what? 1 times 1 times 1, right? Because all inverter, right? The inverter logical effort is always equal to 1. All right, so and what is the B value here, right? Because there's no branch, right? The B is still equal to 1. And H value, H is the output capacitance divided by the input capacitance, right? Which, oh, I'm sorry. Okay, come back here. All right, so then H will be the 64 divided by 1, right? It's still equal to 64. So capital F is still equal to 64, right? But this time small f is equal to f to the power of 1 over n, right? Which is equal to 64 to the 1 over 3, right? So which is equal to what? 4, right? Which is equal to 4, right? 4 times 4 times 4, right? If you use a calculator later, you can do that, right? Small f is equal to 4. All right, if you have the small f being calculated, right, let's go back to this equation, right? D is equal to n times the f to the power of n. This guy is the f, right? Small f plus p, right? This is will be 3 times the this guy plus p, right? 3 times 4 plus total parasitic delay will be what? P1 plus P2 plus P3, right? Which is 3, right? Because all of the gate is the inverter, right? The inverter, the parasitic delay is 1, right? So small p actually. Okay. So what is that? Is the 12, right? Plus 3, right? Which is equal to 15. All right. Getting better, right? It's getting even better, right? So 15. So from 3-stage, all right. And again, we can also back calculate the size of the x and y here, right? So you can still do that. Okay, does it means like if I keep adding the additional number of stage, right? So then the delay time will be keep reducing, right? So yeah, we can do one more round, right? Let's see, for example, this is the case that we keep doing that. Right? Let's adding another inverter, right? Let's still keep the driving and loading as the same capacitance, right? And let's figure out what is the best delay time for this case, right? The equation is not changed, right? The best delay time for any given stage will be the number of stage multiplied by the best stage effort right here, and then plus the total parasitic delay. All right. So we still need to calculate the best stage effort, right, in this circuit, right? In this case, number of delay is equal to 4, right? In this case, previously it's a 3. This is the first stage, right? The first stage is here, second stage, right? And then this is the first stage, right? The second stage, third stage, and fourth stage, right? There's a 4th stage here. Okay, and capital F is equal to capital GBH. And if you do a quick calculation, you will find out this capital F for this particular case is still equal to 64, right? Yeah, so because the G value is not is still 1 and 1 and 1, right? So if you multiply them together, capital G is still equal to 1. B is equal to 1, capital B is equal to 1, right? So there's no branching effort and branching here. So and the capital H is equal to 64 divided by 1, right? So that is the capital F, right? So if you still use this calculation, right, the D will be the 4 times the 64 to the power of 1 over 4, and plus P, right? P will be the will be 4, right? Okay. And if you do that, right, so that is going to be a little bit different, right? 16 point something, right? If I go back to the slides here, let's give the calculation. All right. Oh, yeah, 15. All right. So is my 15 is correct, right? Did I do the correct calculation? Let me go back and yeah, 15, right? Okay. Right. So this is the total, just the best delay I can achieve for a specific circuit, right? So for this case, you'll be able to clearly see that, right? In order to drive a specific loading, right? So uh, single stage not always the best case, all right? In this case, three stage. If I use a three-stage design, the best delay time I can achieve is 15. All right, so it's much lower than the first single stage, right? And yeah, you can see the fourth stage is a little bit higher, right? So I mean the delay time actually increased. The best delay time is actually increased. So it doesn't necessarily means like a more number of stage will be better, right? So there will be a best number of stage for a particular design. All right. So that is what we want to discuss, right? So once you have a design like a target, right? For example, you have a design specifics, right? You know the input, the loading you have, right, from your input stage, and you know your output loading capacitance, right? And then you're gonna design some digital functions between the input and the output, right? You want to design some digital functions. This one give you some, I would say, a very simple design, right? So this one just an inverter, right? You can add in the inverter, right, to invert the signal. But this one, the logic function is simple, right? But if you want to design some more complicated functions, right? So the question here is how many number of stage that I want to use, right? So that I can achieve the best delay time, right? For this particular circuit, right? In this case, it does not mean like a three stage is always the best case, right? If I change this input driver size, or if I change the output loading capacitance, and this best, if I reevaluate this as 4 case or maybe 5 case, right? So then the best delay time may not always coming from the three stage design, right? It may come from maybe 4 stage or maybe come from the 2 stage, right? It depends, right? So because right, if you think about the adding the number of stage, right? The good things for adding a number of stage is yeah, you can drive them right in a way that you can achieve smaller like this stage effort, right? The stage effort can be reduced, so that if you have a multi-stage, the total stage effort is still less than a single stage, right? So if you directly drive that, the stage effort will be huge, right? So it depending on the loading, right? So you don't have any kind of a design buffer right between them, right? So if you're adding more of them, right, so of course you keep optimizing the stage effort so that you can reduce that total delay time, right? But on the other side, if you're adding more buffers, right, adding more stage, right, so you also increase the total parasitic delay, right? So there's some parasitic delay adding additionally, right, to this stage, right? So that is something like you cannot get rid of it, right? So of course there will be some kind of the trade-off, right? So just how can I pick the best number of stage for a particular design, right? So okay, I thought this is a pretty good examples, right? So then yeah, if you don't have it, do you have any questions on these examples? Okay, right. So yeah, if you don't have any additional, let me check the chat message. Okay, good. All right. So let's continue, right? So this is one particular case, right? As I just explained, right? If you have an input capacitance, you have an output capacitance being given, right? You should be able to calculate each of the stage best delay time, right? But for a general case, right, for a pretty general case, if I don't know what kind of the design that I want to have, right, so I don't know the input and output capacitance, for examples, right? So if I try to, if I don't know the topology, for example, right? If I don't know this driver is inverter or maybe internally they use some other gates, right? So for more general case, how can I for example, if I know the input and output, right? So without doing that from single stage all the way to maybe a 10 stage, right? So I calculate each of the case. Can I calculate the best number of the stage by just given the input capacitance and the output capacitance, for example, right? So that is kind of the question that being raised here, right? So if I don't want to do this each of the stage one by one calculation and figure out the best delay time, right? Do I have a design guideline, right, to tell me what is the best number of stage for this particular input and output? All right. So yeah, this is the next kind of a more generalized, the equation that we can follow, right? So okay, so here's more generalized case, right? Assuming that you have a logic blocks, right? You already have a n one stage. This is the at the beginning, right? You have this logical block, right, which already have an n1 stage, and you can add additional number of inverters, right, so that the total number of a stage will be equal to n, right? So capital N, right? So and this is number of inverter is n minus n1, right? Of course, this number of inverter can be 0 or can be 1, can be 2, can be any of the number, right? So this a total stage for your design will be a capital N, right? And your existing block is N1, right? So this is more generalized case, right? For example, I have an N1 stage here at design, right? But and with a loading here, right? The question is this N1 stage with that particular loading, and I know the input capacitance as well, right? So for this case, what is the best number of a stage I should design, right? So that I can achieve the best delay time, right? So I can insert one inverter to become N1 plus one stage, right? I can insert another inverter to become N1 plus two, right? I can insert N minus N, capital N minus N1 stage, right? So that the total number of stages is equal to N, right? So that is the question, right? So can I derive equations, right, from the total delay time, and then figure out if I keep increasing the number of stage, right, changing the number of stage here, one, I can achieve the best delay time, right? For example, D is equal to this equation, right? It's going to be very general for all these circuits, right? So for each of the, no matter what, this total number of stages n, right? So capital N is a variable. Okay, here make sure this capital N is a variable, right? It can be varied from n1 plus one, n1 stage all the way to a small n1, right, to n, right, to capital N, right? So this one means this inverter here, I can either do not add them at all, or maybe add n minus n1 stage. All right, so this is the variable that I can control, right? So the capital N is the number of variable, not number of a stage that I want to design. And this is the equation for the total delay time, right? So Y is a little bit different here, right? Here, path effort doesn't matter, right? So no matter what kind of the how many number of stage I want to insert it, right? So the equation is still valid, right? I still need to use the best stage effort for each of the stage, which is they equal to each other, right? For each of the stage, the small f is always equal to each other, and n number of stage times the small f, and that will be the stage effort, total stage effort, right? The little bit complicated is the parasitic delay, right? The parasitic delay have a two portion. One portion is the existing logic block, right? That parasitic delay, and the additional like inverter, right? When you added where you added additionally to the logical block, right, to become a more number of stage, and that is additional parasitic delay need to be added in, right? So for this logical block, the P1, the PI is the from one stage to the N1 stage, right? The total PI will be just adding them together, right? And then the rest of them will be the inverter, right? The P inverter will be equal to 1, right? So then you have a number of stage which is N minus N1, right, for this inverter. So the total parasitic delay for this inverter portion will be the N, capital N minus N1 times the P inverter, which is equal to 1, all right? Okay, so you may be wondering, right, why I care about this very general equation, right? Because here, a number of n is we want to figure out, right? So once we changing the n to from n1 all the way to yeah, a very large number, right? So this d will change with the n, right, with the number of stage. So in order to find the smallest d, right? So once I change the n number of n, right? So I can do a derivative, right? The derivative, the partial derivative of d, if I divide, I mean, you can see the partial derivative d and to the number of stage, right? So you can do the derivative of this n, right, in this equation, and you will get this. All right, so I will skip all the math stuff here, right? And you can see this is you have n here, right, to the f to the power of 1 over n here, and you have n here, and yeah, you do the derivative of n, you will get this guy, right? So, and this also n here, right? This is a constant value, so this one be gone, right? So if you have an n here, derivative of n will be the p inverter, right? So this will be the equation, right? In order to get the smallest d in terms of the number of stage, I want to get this derivative of n, right? Is equal to 0, right? So that means, okay, so in that case, right, so the n, right, so I get the, in order to get this one equal to 0, I will get the best number of the stage, right? Means this, and with this smallest number, I can achieve the with this particular number of a stage, I can achieve the best, the smallest n number, right? So thinking about the n is, yeah, if I go back and draw the plot, right? Here in this case, you were able to see that, right? If you draw the delay time versus the number of stage, right? So we have the first stage is a 65, right? And you have a 18, and you have a 15, and then you have a 15.3, right? So it's something like this, right? So the delay will be something like this. You have this equation, delay time versus the n, right? In order to get the best delay time, best stage number, right, to achieve the least delay time, you get a derivative of the d versus the n, right, and the slope is equal to 0, right. On that particular point, you should be able to get the number of n, right, the best number of n, right. So that is all the equation tell you to do. Okay. So that is the equation, a little bit complicated, right? So then if we use this equation equal to 0, we should be able to get just a number of n in terms of the the total stage effort and the parasitic delay, all right? So, I mean, this one can be assumed equal to 0 and, I mean, equal to 1, right? This is a P inverter is equal to 1, and the rho is equal to f to the power of 1. This is actually equal to f, right? The best stage effort. So the P inverter plus the f, the bracket 1 over along the just the rho, which is the f, is equal to 0, right? Do some calculation, right? So let's give a definition of f here. In the end, you should be able to get this this equation. Yeah, the problem here, we cannot have the direct solution for that, right? So you do some like iterations, right, to pick the assuming the parasitic p inverter equal to 0, and you should be able to find a best rho value. Right? Rho value is actually the f value, the stage effort value. All right. So in order to get a stage effort values, right, which is f, right? So And if the for f equal to 1, we can solve the rho equal to 3.59. All right, so typically it's the just that is the best stage effort, no matter what condition is, no matter what the input and output value here, right? So if we want to, if we can make the best stage effort f, yeah, which is rho here, right, equal to 3.59, then we should be able to achieve the least delay time, right? The d is equal to the minimum value, right, for this design. Okay, so here is the plot for the d versus the n, right? So with the different number of rho values, right? So for the rho value between the 2.4 and the 6, right? So here the rho is not capital N, right? So this is not the number of stage, right? We try to figure out the best the stage effort, right? If we can figure out the best stage effort, then using the best stage effort, we should be back calculate the number of a stage, right? Okay, I'll show you later, right? So now is, let's see what is the rho number, right? So here, if you changing the rho value to 2.4 to a 6, right, you will get the d is changing versus the rho value, right? So and if the rho value is within this range, 2.4 and 6, right? I mean the delay time is changing is within like a 15%, right? So, and you can tell a little bit from the first case that we used here, right? So the rho value, rho is actually what do we care is the f to the power of 1 over n, right? So which is 5, I think. So if we keep the 5 right in this range, right, 4 or 5, right, in the 2.4 to the 6 in the range, the total delay time change is not that much, right? So it's going to be a small, right? So we should be able to identify the best stage effort by identify the best rho value, right? Okay. All right. So I like a rho equal to 4. All right, you can also pick a rho equal to maybe 3 or 5, right? So that's the total delay time to the rho value change will be pretty similar, right? Will be very small, right? So if we just pick the rho equal to 4, right? So what does that mean? Rho equal to 4 does not tell you, okay, the best number of stage is 4. No, right? Rho, the definition for the rho is here, is this guy, right? It's my stage effort. Okay, so let's come back to my drawing here. I remember you have calculated several times. This is actually my rho value, right? This in this case, rho is equal to 4, right? So yeah, for this case, right? So this is the rho value. This is a rho equal to 8, right? And for this case, sorry, I have the this case. Yeah, this is the rho value 8 and 4 here, right? So they keep changing that, right? If we pick the rho value equal to 4, right? So that means this is the design, right? So this is the design we used last time. Rho equal to 4, right? Means f to the power of 1 over n is equal to 4. Okay. If you pick this value, if we pick this value, that means as long as for a specific design, if I can calculate the capital F, I should be able to back calculate the best number of stage n here with this equation. Okay, so let me say it again. All right, the conclusion we draw before, right, with the very complicated equations, right, very generic equations, we derive, if we keep the rho equal to 4, right, the d will give me the minimum, will be the minimum, right? With the delay time will be the minimum. All right, so that's the conclusion, right? So if we try to make the best stage effort equal to 4, I will always achieve the best delay time. All right. So for one particular case, right, the rho is equal to f to the power of 1 over n, right? For one particular case, if we're able to calculate the f values, right? For example, f is 64, right, to the power of 1 over n equal to 4, right? If I can use this equation to get my n number, right? So I should be able to get my n number out of this equation, all right? So that is the case, okay? So let's go back to the examples, right, to see if we can deal with the examples that we have met in the beginning, right? Right, remember, this is the designers, right? Try to design a decoder, and here's the loading, right? So in order to design the best delay time for this decoder, right, we need to figure out the number of a stage, right, we want to use, right, for the decoder, right? The decoder can be a simple circuit like, I mean, let me just refresh our minds, right? So this is a 4 to 16 decoder, right? You have this A3 to A0, right? And also have A3 not to A0 not, right? So this is a total 8 input here, right? So but you have a complementary input, right? For the A3 to A0. So this is a 4 to 16 decoder. You have a 16 output, right? So for each of the one pass, for example, from one input, right, A0, right, to the one output, right? Let's try to figure out what is the best delay time, right, through this decoder, right? Not the register. Register is our loading. All right, let's make it clear, right? Register is our loading, and decoder is the circuit that we want to design. All right, okay. We know the size of the, here's the definition, right? So there's a bunch of just statements to define the register size, the 32-bit wide, and each bit loading of a 3-unit size transistor. That basically tell you the loading capacitance. All right, we will figure out that later. And to give you the inputs, right, and to give you the driving transistor size, 10-unit size transistor, right, means each of the input capacitance, right, is 10, right? The input capacitance is 10, and the output we can calculate that as well, right? You have 16-bit line, 32 times 3, right? So that would be your output capacitance, right? So you have the input capacitance, you have output capacitance for this decoder, right? And you may be wondering, what is the decoder schematic, right? Should be looks like a block level diagram, right? What kind of transistor that we want to use, right, for the for the decoder. Okay, so let's refresh our mind, right? So let's refresh our mind to see what is the decoder design going to be looks like, right? This is the n to the power of 2 to the power of n decoder. This slides I directly copied from the sophomore level class. All right, yeah, you had it 2 years ago. Okay, this is active high and active low, right? So let's pick one of them, right? For example, active high outputs, right? So this is the 2 to 4 decoder, right? If you have a control, 2 to 4 means you have 2 control pin and the 4 outputs, right? So for our case, we need like a 4 to 16, right? We have 4 inputs and the 16 outputs, all right? So that is the difference, right? But the concept is similar, right? So you have a control pin, depending on the control pin combinations, right? The output will be activated, right? Or will be enabled, right? Specific output will be enabled depending on the input combination, right? Depending on the input combination. So for this case, right, the 2 to 4 decoder, well, when the S0 and S1 equal to 0 and 0, the output from D3 to D0 will be a 0, 0, 0, 1, all right? So if the input combination becomes 0 and 1, the output combination will become 0, 0, 1, 0, all right? So it periodically kind of enable or just set the output, right? Specific output, right? So yeah, if the 0, 0, it will set the D0 equal to 1, and the rest of the output will be a 0, right? And 0, 1 will give you the D1, right, equal to 1. All right, so that is the decoder, all right? You can also separate them out for, like, let's say, for example, 2 to 4 decoder. You can have 4 separate like a truth table, right? So this is one truth table here, 2 input, 1 output, right? So you can get a circuit out of it, right? So basically, if you have this truth table, you should be able to get a equation out of it, right? So so let's do that together. Yeah, let's use this as the example. Right, so and D0, D3, D2, D1, and D0. Right, so 0, 0, 0, 1, 0, 0, 1, 0. Okay, so this is the truth table you have, right? And this is the input, right? This is the out. You have multiple outputs, right? So if I try to get an equation of D0, right? D0 is this outputs. What is the D0 should equal to? See the here, right? So you have this truth table here, right? So this is the input and this is the outputs, right? So finding out the output equal to 1 and write down the equation. This is the S1 naught and S0 naught, right? So because this is the, yeah, this is 0, right? And this is 0, right? So D0 should be equal to S1 naught and S0 naught. And D1 is equal to what? D1, if you look at this line, right, D1 is here. So finding this S1 naught and S0, right? So, and D2 is S1 and S0 naught, right? And S3 is S1 and S2, right? S0, sorry. Yeah. Okay, we have the equation here. Once you have the equation, right, this is one particular output. So what is the circuit kind of looks like? You have a S1 here, right? So you have the okay. So S1, right? So you need to go through an inverter, right? And then S0 goes through an inverter, right? And it goes to an AND gate, right? To this is the D0, all right? And if you keep doing that, and so D1, what is the D1 gonna looks like? D1 is the S1 naught here, right? And S0 here, have inverter here. And you have an AND gate here, right? Okay. And we can keep doing that. So D2 is what? D2 is S1 and S0 naught, right? S1 and S0 naught. S1 here and S0 naught here, right? This is the D2. All right. And the D3. D3 is what? S1 and S0. Right? So you have S1 here and S0. Okay. So you have a circuit, right? So and yeah, if this one is not very clear, right? So you can redraw it, right, to the input of the 3 AND gate. Something like this, all right? Let's do this, all right? D0, D1, D2, D3, right? So let's label this input, right? Because you know, remember, go back to the case that we have here. Right, this all the input here, right? All this input here has been given, right? All the complementary input has been given. So you don't have to add additional inverter to generate a naught, all right? A3 naught or A2 naught. It's been given, right? So that we can come back to our design here, right? Just label the, just use the complementary input directly. This is 2 to 3, right? But let's use the example. This is S1 naught. This is the S0 naught. This is the S1 naught, S0, S1, S0 naught, and we have the S1 and S0. All right. So that would be a circuit, right? This is going to be your outputs. Loading, we know that, right? For each of the output loading, we should be able to calculate. Is given, right, by the customer. The question is, right, how can I design this circuit so that it have a least amount of delay time, right, from one particular input to the output, to the one output, all right? So yeah, the example we have just go through, right? So f to the power of 1 over n is equal to rho. Let's keep the rho equal to 4, right? So that means I want to have my best stage effort, right, equal to 4 to achieve the to calculate the number of n, right? So what is the f value here? F is the GBH, right, for this circuit. GBH is the value that we want to calculate first. And then once you have this value, you put in here, and then use the rho equal to 4, and you can back calculate number of stage, right? So now you see the problem here, right? Okay, that's assuming, right, the design here, right? So this inverter, so this is a NAND gate, right? So it's actually a 2-input NAND gates. We should be able to calculate the G value, right? And you can add in the inverter in there, right? G value will not be changed, right? So I can calculate the G. And what is the B value here? And what is the, okay, let's skip the B for a while. H value should be straightforward, right? Because we know the output capacitance value, right? 32 times 6. And we do the input capacitance value, which is the 10 that is given, right? So we should be able to calculate the H value as well, right? So the G and H can be calculated. But the B, the branching effort, is pretty tricky here. What is the branching effort? Does anybody know the branching effort for our case? So for this case, what is the branching effort? This is the 2 to 4 decoder, right? 2 to 4 decoder. What is the branching effort here? Is it 1? Yeah, if I draw it in this way, you might not be able to see it very clearly, right? But if I use the inverter as my loading, right? Inverter as my loading. This is a loading here. Sorry, this is a driving, all right? Inverter as my driving capacitance, right? Which is always equal to 10 or something, right? And you have a S1 output here, and this one is connected to here as well, right? And S0 is connected to here as well. So you will see each of the input is actually connected to two outputs here, right? So this first stage, they will have some branching here. For S1, right, you have some branching here to the, sorry, S1 naught, you have some branching here as well, right? So S0 naught, when loading is here, right, you have another guy here, right? So you can always find a branching here, right? So what is the branching effort in our case? Okay, let's go back to discuss that. All right. Okay, this is the circuit, right? So electrical effort, right? Pretty straightforward, right? 32 times 3 that is being given, divided by the input, right? Which is 9.6. And G, let's assuming G is equal to 1, that is a very bold, a very rough estimation, right? Because, you know, yeah, you can argue that the NAND gate, right? If I use NAND gate, the logical effort is not 1, right? So like a 4/3 or something, right? It's a little bit over 1, right? So but if we use a different topology, if we use a different like just gates, right? So then the logical effort will be different, right? So I mean, this a gate can be changed, right? I can use a NAND gate, I can use an AND gate, I can use a NOR gate, right? Those gates can be changed as well, right? So so in order to have a first order of estimation, let's assuming G equal to 1, right? So GBH, so that's can be estimated, right? The difficult part will be this B value, all right? So why the B value is equal to 8 in this case? Why there's an 8 branch here for each of the inputs? So anybody know that, right? For this 2 to 4 decoder, for example, right? Yeah, we have actually 4 inputs, right? S1, S0, S1 not, S0 not. And there's a total 8 of them here, right? 8 inputs here.
Is it due to the number of on-path and off-path gates that are in the circuit?
Yes, yeah, but why is the number that passes equal to 8? And that is the question. Okay, yeah, I think yeah, let's leave this question to you and think about it, right? We can pick it up the next this Thursday, right, to discuss the branching effort, right? So think about this case, 2 to 4 decoder. What is the B value here, right? And if we have a 4 to 16 decoder, right? So what is the branching effort here? Okay. Yeah, in this case, I think the B value is equal to 2, right? So then for the 4 to 16, right, the B value is equal to 8. Right, so yeah, but we will figure out, right? We will talk about it more in the next class. All right. So the Thursday we will have the same format. Right? I'm still in Phoenix here. We will do the class online through the Blackboard. Right. I posted the homework 3 online already. Right. I kind of extended that the deadline to next Tuesday. Right. So you have enough time to finish that. Yeah. Next Tuesday is the spring. Sorry, it's a fall break, right? So, I mean, you can turn in a little bit earlier, no problem, right? But yeah, turning that, even though we don't have a class, right, on that Tuesday. Okay, all right. So let's finish the class today, and then we will meet on the day after tomorrow, on Thursday. All right. Thank you.